Welcome to the Before AGI podcast, everyone. We're diving deep into the world of AI again today. And specifically, we're going to be talking about how we can take these really powerful AI models that everyone's talking about and actually get them to run on, the devices we use every day.
It's a great point.
Like our phones and our smartwatches and even those, smart sensors we might have around the house.
Exactly. And it's funny because, we're building these AIs that are capable of just incredible things.
Right.
But a lot of the time, they require the processing power of like a whole server farm.
Right.
So how do we bridge that gap to get them onto the, the devices that that we use every day with limited resources?
Yeah.
That's kind of the core challenge that we're tackling today, I think.
Yeah, absolutely. I mean, just think about wanting to have real-time translation right there as you're talking to someone.
Yes.
Or, keeping your health data private on your wearable. Yeah. So today we're going to be focusing on AI model compression and quantization, which are like the keys to making that happen.
Absolutely.
Right?
And I think, this is really not some sort of abstract problem because the demand for AI on edge devices, which are like your smartphones, the whole IoT ecosystem you might have around your house, is exploding.
Right.
But, these devices, they have limitations in terms of their computing power.
Right.
Memory and battery.
Yeah.
And, modern AI, particularly like deep learning and these massive large language models, are getting bigger.
Mm-hmm.
I mean, some of them can be tens of gigabytes in size.
Yeah.
It's like trying to fit a supercomputer into the palm of your hand.
Yeah.
So that's kind of the central bottleneck.
Yeah. So what are some of the ingenious solutions that we've come up with to actually make this happen?
Yeah, well, the answer really lies in two vital techniques.
Okay.
AI model compression and quantization. Compression at its heart is really about, making an AI model leaner.
Yep.
So reducing its size and computational complexity. And then quantization, which is a specific type of compression and a very powerful one, really focuses on how the model represents numbers internally. So like its weights and activations.
Okay.
Instead of using like a very precise 32-bit floating point number, we're talking about using lower precision formats like 8-bit integers.
So it's kind of like, I guess if you were describing something with very, very fine detail versus just using broader strokes.
That's a perfect way to think about it.
You lose a tiny bit of nuance, but it becomes much easier to kind of manage.
Absolutely.
Yeah.
And the benefits for edge AI, for AI on your devices, are really substantial.
Yeah.
First off, you get reduced latency.
Okay.
Which means faster processing, quicker responses. You get improved privacy because your data stays on your device. You optimize bandwidth because you're not sending information to the cloud constantly. And crucially, you become less reliant on a constant internet connection.
Yeah. And I mean, here's where it gets really interesting.
Yeah.
Some projections are saying that by 2025, the vast majority of enterprise data will originate from these edge devices.
Absolutely.
So up to 75%.
Yeah.
So, I mean, that really underscores why processing locally on the device is going to be so critical.
Yeah. And that brings us to the first kind of key tool in our arsenal here.
Okay.
AI model compression. So to kind of define what we're trying to achieve here, model compression aims to reduce the size and computational demands of AI models after they've been trained.
Okay.
And whilst trying to maintain, a high level of performance, so accuracy and reliability.
Yeah.
And it's important to note that this is different from something called knowledge distillation, where you actually train a brand new, smaller model.
Gotcha.
So it's really about taking an existing model and making it more efficient. And for edge devices, the advantages are pretty clear. Smaller models require less storage space, very critical when your phone or smartwatch only has so much memory.
Right.
They use less RAM when they're running, which means smoother performance, potentially.
Right.
And faster processing, of course, means quicker responses for you. And then, of course, reduced power consumption means better battery life for mobile devices.
Yeah.
Big one for everyone.
Right.
And importantly, I think it's not just about the flagship devices that you might own. Compression can enable AI on, more basic, lower-end devices that wouldn't otherwise be able to handle these complex models. So it's about expanding the reach of AI.
Right.
And I think simplifying the deployment across a wider variety of devices, as well as reducing our dependence on constant cloud computing.
Okay, so let's actually talk about like how we shrink these models.
Yeah.
So what are some of the main techniques that are like in our toolkit here?
Well, there are several key approaches here. So let's start with pruning. So imagine a fully trained neural network. It's like, this vast network of connections. Pruning is essentially like carefully removing the less important or redundant connections in that network.
Okay.
So slimming down the network. It's like decluttering for AI.
Right.
And there are different ways to prune. So you can do weight pruning, which is like removing individual connections that are less significant.
Okay.
Then there's neuron pruning, where entire neurons are removed. In convolutional neural networks, which are very common in image processing, there's something called filter pruning, which is about removing entire filters.
Gotcha.
And then, in more extreme cases, you might do layer pruning, where you remove entire layers of the network.
Wow. Okay. So now I know we were talking a little bit before the show.
Yeah.
And I remember reading about something called structured versus unstructured pruning. Can you kind of talk about that a little?
Yeah, I think this is a really important distinction for practical deployment of AI.
Okay.
So unstructured pruning is kind of like removing individual threads from a piece of fabric.
Okay.
You can remove a lot of material, but the remaining structure might be like irregular.
Right.
And difficult for kind of standard processes to handle efficiently. Structured pruning, on the other hand, is like removing entire rows or columns.
Okay.
So larger, more organized chunks. While you might not achieve the same level of overall reduction,
Right.
the remaining structure is much more regular.
Gotcha.
And easier for the underlying hardware to process quickly.
So I guess structured pruning is like generally better if you're looking for like actual speed improvements.
Absolutely, yeah.
Because it just aligns better with how the hardware is designed.
Exactly.
Okay.
And pruning, just to kind of recap, it can actually happen either during the training process itself or after the model has been fully trained.
Okay, cool. So that was pruning. So that's one way that we can kind of slim things down. So what about, you mentioned knowledge distillation earlier.
Yeah.
Can you talk about that a bit?
Yeah, knowledge distillation is a really elegant approach. So imagine that you have, a very large, highly accurate teacher AI model. This is like, you can think of this as the expert.
Right.
And knowledge distillation involves training a separate, smaller student model to learn from this teacher.
So like the student is kind of like trying to absorb the teacher's expertise.
Exactly. The student learns to mimic the teacher's behavior.
Okay.
And not just its final predictions, but also kind of the more nuanced ways it arrived at those predictions. And this allows the smaller student model to potentially achieve performance that's surprisingly close to the much larger teacher.
Wow.
But with significantly fewer resources.
That's so interesting. And are there different ways that we can actually like do this knowledge transfer?
Oh, absolutely. There's response-based distillation, there's feature-based distillation, and there's relation-based distillation, each focusing on transferring different aspects of the teacher's knowledge.
Okay.
And they can be done, offline, online, or even self-distillation. So lots of kind of flexibility in how you do this.
Gotcha. Okay, so we've got pruning to kind of trim the fat. We've got knowledge distillation to learn from the best. What's the third kind of compression technique?
Okay, so the third one is called low-rank factorization.
Okay.
This is a bit more mathematical. But basically, think about all those large tables of numbers, the weight matrices, that are within a neural network.
Right.
Low-rank factorization uses methods like singular value decomposition, or SVD, to approximate these large structures with smaller, more manageable representations.
So it's kind of like finding like a more concise way to represent like the same like complex information.
Precisely.
Yeah.
And by using these lower rank approximations, you reduce the number of independent parameters in the model, which directly leads to a smaller model size.
Gotcha.
And in some cases, can also speed up the calculations when the AI is running.
Cool. So those are kind of the main ways that we make AI models smaller. So let's move on to the second key concept, AI model quantization.
Great.
So what's the core idea here?
Well, quantization takes a bit of a different route to making models efficient.
Okay.
Instead of focusing on the network structure, it really focuses on the precision of the numbers that are used to represent the model's parameters and activations.
Okay.
So that, the very fabric of the AI's calculations.
So like the weights and like the signals that flow through the network, like the fundamental data that's like powering the AI.
Exactly.
Hmm.
Typically during training, these values are represented with high precision 32-bit floating point numbers.
Right.
And quantization reduces the memory and computational demands by representing these values with lower precision numbers, like 8-bit integers.
Okay, so that's like a pretty significant like reduction in precision.
It is.
Does that like impact the accuracy of the model?
Well, that is the central challenge here.
Okay.
So while quantization drastically reduces memory usage and it speeds up inference because integer math is much faster
Right.
and can lower power consumption, we have to be careful to minimize any loss of accuracy.
Yeah, yeah.
And so there are a couple of different ways, of implementing quantization.
Okay.
There are two main forms. Post-training quantization, which is often abbreviated as PTQ,
Okay.
and quantization-aware training, which is abbreviated as QAT.
Okay.
And post-training quantization is pretty much what it sounds like. You train the model as usual with high precision,
Right.
and then you apply the quantization afterwards. It's simpler, it's faster, but it can sometimes lead to a bigger drop in accuracy.
Okay.
And then there's quantization-aware training. And this method actually integrates the quantization process directly into the training.
So the model is like learning to function effectively even though it's in this like lower precision environment.
Precisely. During training, QAT actually simulates the effects of quantization on the weights and activations.
Gotcha.
And this allows the model to kind of adapt and learn to compensate for that lower precision.
So I guess like PTQ is like the kind of faster route to, getting a smaller model. But then QAT is like the more refined approach to kind of maintain like better accuracy.
That's a great way of summarizing it.
Yeah, cool. Okay, so let's talk about the real kind of like impact that these compression and quantization techniques have on the size and speed of AI models.
Yeah.
So like, what are the improvements that we're actually seeing?
Well, the impact can be really quite significant. So on the compression side, pruning directly reduces the number of parameters and the complexity of the model, leading to smaller and faster models. Knowledge distillation inherently creates smaller models from the start, and low-rank factorization reduces the amount of data that needs to be processed.
Cool. And then quantization also like directly impacts that, right?
Absolutely. So when you reduce the number of bits used to represent each parameter and activation, so going from 32-bit to 8-bit, for example, you get a direct 4x reduction in model size.
Wow.
Plus, lower precision math is significantly faster and more energy efficient, which leads to quicker responses and longer battery life.
Right.
We're talking about INT8 quantization, potentially reducing computational costs and power by around 40%, and INT4 by even more.
Wow.
And, hardware has been shown to see, 2x, 3x speed improvements when you're using these lower precision formats.
Those are some pretty substantial gains.
Yeah.
And so I guess what's really exciting is when you kind of combine these techniques together.
Oh, absolutely.
Yeah.
So, using compression and then quantizing the already smaller model can lead to some like really impressive results.
Yeah.
Studies have shown, up to 90% reduction in model size and computational requirements.
Wow.
With very little impact on accuracy.
That's amazing. But with all these advantages, I imagine there must be some trade-offs to consider.
You're absolutely right. It's a delicate balancing act.
Okay.
So the primary trade-off here is often between, on the one hand, model size and speed gains. And on the other hand, maintaining a high level of accuracy.
Right.
Push too hard on making the model smaller and faster, and you risk negatively impacting the quality.
Yeah.
And, with each technique, there are, specific trade-offs that we have to consider.
Okay.
So with pruning, aggressively removing connections can lead to accuracy drops. Quantization's lower precision can also introduce inaccuracies. Knowledge distillation requires careful training to ensure the student model actually learns effectively from the teacher.
Yeah.
And with low-rank factorization, the accuracy kind of depends on how well the lower-rank representation approximates the original.
Right.
So developers really need to carefully navigate these trade-offs to deliver the best possible experience.
Yeah. Yeah. So how do you go about like deciding like which approach or combination of techniques is going to be best?
Well, it really depends on kind of the specific limitations of the device that you're working with and the requirements of the application.
Okay.
So for very resource-constrained devices, some accuracy loss might be acceptable
Right.
if it means that you get significant gains in size and speed.
Yeah, yeah.
Real-time applications where quick responses are crucial, they're going to prioritize speed. Whereas accuracy-critical apps might lean towards more robust techniques like QAT.
Right.
So it really depends. And often, a carefully tuned combination of methods is kind of the optimal solution.
Right. Okay, so this is all super interesting. So now let's actually talk about, like, where are we already seeing this kind of stuff in action?
Right.
Like, what are the ways that, the technology that we use every day is actually, like, leveraging these techniques?
Well, I mean, you see it everywhere you look.
Yeah.
I mean, think about the face recognition that unlocks your smartphone.
All right.
Or the speech-to-text that transcribes your voice, or the image processing that enhances your photos, or even, virtual assistants that answer your questions.
Right.
These are all powered by efficient AI models running directly on your device.
Yeah.
And, often using frameworks like TensorFlow Lite or PyTorch Mobile.
So, like, the AI features that we kind of rely on every single day are already benefiting from this, like, under the hood.
Absolutely.
Yeah.
And it's not just your phone. So, IoT devices in your smart home, like cameras and sensors, use these techniques for, object detection and environmental monitoring with very limited power. Autonomous vehicles rely on real-time processing of sensor data for safety, which is really only possible with highly optimized AI.
Right.
And even the wearables that you have on your wrist, use compressed AI for health tracking.
Okay, so can you give, like, I guess some specific examples of, like, successful implementations?
Yeah, sure. So, I mean, we've seen, significant size reductions in image recognition models while maintaining high accuracy, enabling much faster and more efficient photo processing on your phone. Quantization is routinely used to deploy these, advanced image classification models on mobile devices, which improves the speed and efficiency of apps.
Right.
Knowledge distillation has led to smaller language models that power faster, more responsive text-based AI features.
Right.
And, compressed models are essential for real-time object detection in things like security systems and, in vehicles. And we're seeing compressed models used in medical image processing, to enable, very sophisticated analysis to happen on low-power devices.
That's really interesting. So looking ahead now, I guess, like, what are some of the exciting, like, kind of advancements on the horizon?
Well, the field is rapidly advancing, I'd say. And one key trend is automated model compression.
Okay.
So where AI algorithms are actually used to determine automatically the best compression strategy for a given task and hardware platform.
So, like, AI is helping to create more efficient AI.
Exactly. We're also seeing significant progress in hardware-aware quantization, where the quantization process is tailored to the specific capabilities of the processors in edge devices.
Okay, that makes sense.
So really optimizing for the hardware.
Yeah.
Researchers are constantly pushing the limits of low-bit quantization, trying to use even lower precision numbers without significant accuracy loss. So this could lead to even smaller and faster AI. There's a growing focus on what's called activation-aware quantization to further minimize accuracy degradation.
Okay.
Hybrid compression techniques, which combine different methods, are becoming more sophisticated. And I think making quantization-aware training easier for developers will really accelerate the deployment of, high accuracy, efficient AI.
Right.
And finally, with the rise of these large language models, there's a lot of interest in compressing these massive models so they can eventually run, at least in part, on more powerful edge devices.
Yeah. So it sounds like there's still, like, kind of some, like, pretty significant challenges, like, that need to be overcome.
Oh, absolutely. Maintaining high accuracy while you aggressively compress models, ensuring compatibility across a very diverse range of hardware platforms, simplifying the implementation process for developers. Those are all kind of ongoing challenges. Efficiently updating models on billions of edge devices and addressing the security and privacy implications of this, kind of distributed AI.
Yeah.
Those are really important considerations.
Yeah. Okay. So this has been a really great kind of deep dive into AI model compression and quantization.
It has.
We covered why it's so essential and, some of the really fascinating techniques that are actually being used to make it all happen.
And I think the key takeaway here is that, getting AI onto our edge devices isn't just about creating more powerful chips. It's equally about cleverly optimizing the AI itself.
Right.
And the advancements in this field are going to have, really profound implications, I think.
Yeah, absolutely. So we hope this deep dive has provided, a clear understanding of this really important area of AI research for you. And for more in-depth explorations of AI concepts and, all the latest advancements, make sure to subscribe to the Before AGI podcast. And if you're interested in getting even more hands-on with AI, be sure to check out my YouTube channel, Ian O'King AI, for tutorials and insights. Thanks for joining us on this deep dive.
Thanks for having me.